Welcome to lecture number 8. So I want to start with a really cool fact. So it turns out all linear transformations can be written as a matrix transformation, provided those linear transformations are from Rn to Rm. And this is a theorem, which I will now include. This is theorem 10 in the book. Furthermore, this theorem tells us how to find the matrix that captures the information of the transformation. And it's going to be T, the transformation to the E1 vector, where E1 is, in a sense, the coordinate vector in the first direction. So J is 1 here, so it has 1 in the x1 direction and 0 everywhere else. And then E2, etc. So these E's you could think of as vectors in the directions, coordinate directions in Rn. In this example, this is R3. Okay, so let's look at an example and we'll find this matrix using the formula here. So suppose we have a transformation from R2 to R2, and it's linear. It's important that this is a linear transformation, otherwise the theorem doesn't hold. And furthermore, we know that the transformation to 1, 0 is 2, 0, and the transformation of 0, 1 is 2, 2. So use linearity, definition of what it means to be linear, to justify theorem 1.10. Okay, so let's think about a general vector, and we're going to consider what the transformation does to this general vector. So we don't know what the transformation does to most vectors. We only know what the transformation does to these two particular vectors. But what's nice about these coordinate vectors, this is like E1 and E2 and R2, is we can represent all vectors as linear combinations of these. So x1, x2 is going to be x1 times the first plus x2 times the second. So if we know what the transformation does to these two vectors, we can figure out what the transformation does to this general vector because the transformation is linear. Let me show you how that works. So if we put this general vector in the transformation, we can replace it with this expression because they're equivalent. And then we can use the properties of linearity to move the t, the transformation, to be acting on just those coordinate vectors. So this is just using the two properties of what it means to be linear to move the t over and, in a sense, distribute it. All right, we know what the transformation does to these two vectors. It turns the first vector into 2, 0, and it turns the second vector into 2, 2. And what's interesting about this is a vector equation that can be written as 2, 0, 2, 2 times x1, x2. And that's just going from vector to matrix vector product. That's just using the definition of the matrix vector product. And now we see that the transformation is a matrix times the vector. And this is our matrix A. And we can see that the theorem holds because the theorem says A is going to be the transformation of the first vector, the first coordinate vector, as the first column, and then the second column's the second what the transformation does to the second coordinate vector. And it only acts on 2 coordinate vectors because we're in R2. So that's A. That's what the theorem says A was, and that's what we found A to be when we used the property of linearity. Let's look at another example. And the formatting of this example is a little different. This is what the textbook uses sometimes when we're talking about transformations. So this transformation is taking a vector, and the vector is written as a row here in R3, has 3 coordinates, to another row in R3. Okay, so typically we would write this, and in the homework you'll see it most often written this way, like this. But we can write it as rows, and it's still true. And just note that this problem calls A the standard matrix, and that's the name for A in words. So when you hear standard matrix or you read standard matrix, think A. So the key to finding the standard matrix, according to the theorem, is to figure out what this transformation does to the coordinate vectors, namely what it does to 1, 0, 0, what it does to 0, 1, 0, let's write it down here, and what it does to 0, 0, 1. And what's nice about this transformation given as a formula is we can see what it does. If we have 1 for the first coordinate, then that 1's going to appear both here and here. So 0, 1, negative 1. If we have 1 in the second coordinate and 0 elsewhere, then that's going to show up nowhere. It's not going to be anywhere in this formula. So that's going to be 0, 0, 0. And then if we have 1 in the third coordinate, that's going to show up here and here. So that'll be 0, negative 1, 1. And that's it. Once we know what the transformation does to those coordinate vectors, we just stick them all together. 0, 1, negative 1, 0, 0, 0, 0, negative 1, 1. And that's the transformation matrix. And you can see that if we just take this matrix and multiply by x1, x2, x3. So the claim is that these are equal, and if we do the work here, if we do the matrix vector product, we'll get x1 times this vector plus x2 times this 0 vector, that one's just gone, plus x3 times this third vector, which is going to be x1 minus x3 in the second coordinate and minus x1 plus x3 in the third coordinate. And these indeed match. This matches. So we are correct in our identification of A. This is the correct matrix, standard matrix.